Welcome to our lesson on conservation of energy. This fundamental principle is one of the most powerful concepts in physics, helping us solve problems that would otherwise be extremely challenging. Energy is the capacity to do work or produce heat. It comes in many forms, but the most common types we'll focus on today are potential energy, kinetic energy, and other forms like thermal, chemical, and electrical energy. The law of conservation of energy states that energy cannot be created or destroyed, only transformed from one form to another. This means the total energy in an isolated system remains constant. Let's first explore potential energy in more detail. Potential energy is stored energy that an object has due to its position or arrangement. The most common type is gravitational potential energy, which depends on an object's height above a reference point. The formula for gravitational potential energy is Pe equals mgh, where m is mass in kilograms, g is the acceleration due to gravity, approximately 9.8 meters per second squared on Earth, and h is height in meters. Next, let's look at kinetic energy. Kinetic energy is the energy of motion. Any object that's moving has kinetic energy. The formula for kinetic energy is Ke equals 1/2 mv squared, where m is mass in kilograms and v is velocity in meters per second. For example, a car moving at high speed has more kinetic energy than the same car moving slowly. Note that kinetic energy depends on the square of velocity, so doubling the speed quadruples the kinetic energy. When we combine potential and kinetic energy, we get mechanical energy. Mechanical energy is the sum of potential and kinetic energy, and in the absence of friction or other non-conservative forces, mechanical energy is conserved. This gives us a powerful equation. The initial mechanical energy equals the final mechanical energy, or expanded. The initial potential energy plus the initial kinetic energy equals the final potential energy plus the final kinetic energy. Let's visualize this with an example of a ball dropping from a height. We have a ball at a height h above the ground. Initially, it has only potential energy. At the initial position, the ball has potential energy mgh and zero kinetic energy. As the ball falls, potential energy decreases while kinetic energy increases. Halfway down, the energies are equal, with each being mgh divided by 2. At the ground, all potential energy has been converted to kinetic energy. The ball now has zero potential energy and mgh of kinetic energy. Let's see how the energy changes during the fall in a different way. We can visualize this with energy bars representing potential and kinetic energy. As the ball falls, the potential energy bar decreases while the kinetic energy bar increases, but the total energy remains constant. The conservation of energy principle appears in many real-life examples. In a pendulum, energy constantly converts between potential and kinetic forms. On a roller coaster, the initial potential energy at the top converts to kinetic energy as the coaster descends, then back to potential energy as it climbs again. In a spring system, energy oscillates between elastic potential energy and kinetic energy. It's important to note that mechanical energy isn't always conserved in real systems. Non-conservative forces like friction convert mechanical energy to thermal energy, reducing the total mechanical energy over time. However, the total energy, including thermal energy, is still conserved. For example, a pendulum eventually stops due to air resistance and friction at the pivot, but the lost mechanical energy is converted to thermal energy in the air and pivot. The conservation of energy principle is a powerful tool for solving physics problems. Let's solve a problem. A 2-kilogram block slides down a frictionless ramp from a height of 3 meters. What is its speed at the bottom? We can use conservation of mechanical energy since there's no friction. Initially, the block has only potential energy. mgh equals 2 kilograms times 9.8 meters per second squared times 3 meters, which equals 58.8 joules. At the bottom, the block has only kinetic energy, 1/2 mv squared. Since mechanical energy is conserved, we can write 58.8 joules equals 1/2 times 2 kilograms times v squared. Solving for v, we get v equals 7.67 meters per second. Let's summarize what we've learned about conservation of energy. Energy exists in different forms, including potential, kinetic, thermal, and others. The law of conservation of energy states that energy cannot be created or destroyed, only converted from one form to another. In the absence of non-conservative forces, mechanical energy, the sum of potential and kinetic energy, is conserved. Non-conservative forces like friction convert mechanical energy to other forms like thermal energy, but the total energy is still conserved. Understanding energy conservation gives us powerful tools for solving physics problems that would be difficult using other methods.